Everyone, we're going to get started. Hope you've all had a nice little extra day off for the math. And what I want to do today is continue with section 2.7. We'll see how it goes. I'll make no predictions. Right, jump right into a question. And this is similar to question 7. We've got a square root function, and we're being asked to find the slope called m at this given point. It's fine. Now, the 3 lines that you can see here are definitely not enough to do this. The way that you would solve this, I'm just not going to do it because it takes a lot of time, is couldn't we use the limit as h tends to 0 of f of ah, take away f of a over h, and couldn't we use that and replace the a with a -5? And can you imagine that that would be quite a long question, and you probably end up using the conjugate method and you get your answer. Or you could use the limit as x tends to a, in which case the formula for finding the slope m would be this guy. Now, both of these are finding that slope. So I'm skipping that bit. You would have to do that, but that would be, whatever it is, 15 minutes work. I'm going to cheat a little bit. I should have planned ahead, but I forgot to. I'm off screen. I am actually doing a shortcut for finding that. You're not going to find out about that shortcut quite yet. And the slope of this fella here ends up being -2 over the square root of 25. So it ends up being -2/5. And you're just going to trust me that that guy there is -2/5. Right? You'll eventually prove it, but that's what it is. So once you've got the slope m, then you find the equation of the tangent line at this particular point here. And I'm going to be using pretty much this equation every single time they say, find the equation of a tangent line at a given point. In this case, it's going to be y take away 5 equals -2/5. Well, if you take away a negative, it's essentially adding it. So I get -2/5 x, that looks like it'll be -2. So the final answer I would get by adding 5 to both sides would be that. So just a little warm-up of one of the most common questions they've got in this section is find the slope of the tangent line m, and then use that slope to find the equation. So the key here is the equation of the tangent line. And if you know the slope at a given point, in this case it's -2/5, you'll use this formula here to get the equation of the tangent line. Now, if you wanted to check it, you'd probably find, where would that be? It'd probably look like this. This is what the curve would look like. And if you found this tangent line, that's not the curve. There, that's the curve. And if you found a guy at -5, that would be this fella here. And so you could actually put it into your calculator and use that as a check. So that's pretty much the basic question. Find the slope of the tangent line and then get its equation. Now, there's a whole bunch of questions that's exactly what happens. I'm going to show you how we can do that using, I'm just calling it the shortcut method right now. It's actually the power rule. So question 8, at least in the version I've got, you get y equals 8 plus 5x squared, take away 2x cubed. And we've been asked to find the slope of the tangent line at x equals a. Now I could certainly do that using these two formulas. Even for a very small polynomial, don't those things take forever and a day to do? Can you imagine it would be x minus a all cubed here, x minus a all squared, a whole, it'd end up about this big, and then it would get a little bit nicer, and then you take it, 15 minutes later. But we can avoid that because we have a shortcut. A little side issue. I don't think this is a big deal. I hope it isn't. That isn't when you say y equals, isn't that totally equivalent to saying f of x equals? Right. So, using the shortcut, let's find f dashed of a, because that's basically going to be our slope, right? Okay, let's see. The power rule says you multiply by the power and you reduce it by 1, okay? Numbers like 8, don't all constants disappear, right? You don't get anything out of them. Everything else, you can use a rule. So multiply by the power and then reduce the power by 1. For this one, multiply 3 and -2 together, it gets you -6 a squared. And that, the guy there, I guess I should write it maybe a bit more mathematically. Yeah. There we go. We got the answer in seconds rather than 15 minutes. And that's part A. And part B says, find the equation of the tangent line at 111. Okay. So at the point 1, 11, I'm going to find the equation of the tangent line. So I need to know what the slope is at this point. And that guy is A. A is the x-coordinate. So it's 10 lots of A. Take away 6 lots of A squared, and the answer is 4. And now I can finish by the point slope equation. And it's going to be y take away 11 equals 4 x take away 1. And the next few lines are pretty standard. Not doing anything particularly clever. And we are good. Do you see how smooth the process is for finding the equation of tangent lines when you can use the shortcut, the power rule? Because the piece that would take you the longest would probably be to find this answer, right? To find the slope of the tangent line at a given point, x equals a. Well, I guess I could have done it at x equals 1, but in this question, they asked you to do it twice. Now, I'm not going to do that one, but would you agree that one would be very similar to how we did this one? So far, so good. So as long as it's a polynomial like this, we can use the shortcut, the power rule method. Okay, you kind of hit list. I'm not doing this question. This is question 9. You're going to do it to square it out. You're going to have to do question 9 the long way. That's all I'm going to tell you about that one. Let's look at question 10 now. This here is our essentially our first application. This represents someone jumping off a 50-foot cliff. And the distance he falls after t seconds is given by this formula. And the first question is nothing to do with calculus. The first question says, which of these equations would you use to solve for t, which is the time it takes a diver to hit the water? So the distance that he has traveled after time t is given by 16t squared. He's at the top of an 80-foot cliff, right? Off he goes. If I want to know how long it takes him, right? Say he might be there at the 1 second mark, right? He might be there at the 2 second mark, right? He might be there at the 3 second mark, right? I want to know how many seconds before he reaches, right, the sea. I don't need to know the answer, but what would be the equation I would use to solve this? Just algebra. Everything you need to know is here and here.
16t squared minus 80.
Okay, so what you said is totally correct. Just write it in that format. Because that's the choices you got in the answers, right? Would you agree that when that happens, that's when it hits the ground? Now, if you rearrange that, you could say, solve that equation, which is what Kelsey was saying, I believe, right? But let's do this one, which means then I can now find out how many seconds it takes. Now, it depends on what you've got, the approach to solving the equation, but one of the techniques I use an awful lot is as long as you do it to okay, as long as you do it to both sides, it's okay rule, which is my made up name for it. So what should I do to both sides to try and solve for t?
Divide by 16.
And probably, although it's not algebra, I should probably try and simplify that. Would you agree? So divide the top by 8. Wow, we got lucky. 5. Okay. Now, technically speaking, when you take the square root of both sides, you get plus or minus square root of 5. But in the context of this story, unless you believe in Doctor Who and time travel, well, we assume that t is a positive number. And so it's only going to be the square root of 5, which is what, 2.2, 2.3 seconds. So it's not a long dive. We got that. So it then goes on and asks us to find the velocity. And you're looking and you're saying, where the heck did that come from? We've never done velocity. Well, the slope of dt at time, what do they want? T equals a. So they want us to find the velocity at t equals a. At t equals a is the same thing as the velocity at t equals a. So let me try and prove that to you. This is just in general, right? Okay, imagine you had a curve that represented time against position. If you choose any point on that curve, let's say here at t equals a, what you're looking at here, very badly drawn, is what I think the tangent line might look like. Okay, let me curve that thing out of the way so we haven't got it. The slope of that tangent line is rise over run. If I add in some extra little lines, isn't the distance, that distance, the distance in position? And this one going that way is a change in time. And isn't velocity from your physics class you ever seen that, the rate of change of distance with respect to time? So the slope of a tangent line represents, in this context, velocity. It's a rate of change. It's how your position is changing through time. So there's a reason you might want to find the slope of a tangent line. Suppose I did a time velocity curve, right? So I found the velocity of a moving object at any given time. If you find the slope of the tangent line, what do you call the rate of change of velocity with time?
Acceleration.
So can you see that if you find the derivative of a velocity function, aren't you also finding the acceleration at that point, the instantaneous acceleration? That's kind of cool. It's a side issue, but this is kind of cool, so I'll do this a little bit more. Suppose I told you that I had an object and its position was given by this formula. If I wanted to find its velocity at t equals a, wouldn't it just be 18a plus 4? That means if I know where you are at any given time, don't I also know how fast you're going now at any given point in time? And I could, with a little bit of math, couldn't I turn that guy there into, I guess I should put an E here, by the way. Couldn't I take this guy and find its derivative, and wouldn't that tell me it's instantaneous acceleration? Another side issue. I'm just showing you why finding derivatives right now are good, so it's kind of side issue. Nah, wait, I'll keep that one. That's a good one, but I'll keep that there. Right. Don't want to drift too far away from the goal. So can you see that in this question, we're now back to question 10, that you can find velocity, you can find acceleration, you can find anything you want by simply just finding derivatives. So if you tell me position and I find its derivative, I get velocity. If you tell me velocity and I get its derivative, I get acceleration. So this one, oh, I didn't do that, did I? No, I didn't. Oh, I should do the answer then. Can we use the shortcut on this one? What is the shortcut for the derivative? I keep putting t here, but really I should be putting a, shouldn't I? What is the derivative of this guy at t equals a? Shortcut method.
32a. Or 32t,
Right.
whichever you want.
Well, yeah, if you want to call it. We're going to get rid of those a's very soon, thank goodness. Can you see the a is just a placeholder? Couldn't I have called that d dashed of t as 32t, and it'd probably be easier in our brain. But we're kind of keeping it consistent for the homework. Yeah, and if I happen to know that it hits the ground at that time, won't the velocity when it hits the ground be 32 square root of 5? So I even now know what the number is. Before I move on, any questions about that? I know I drifted a little bit, but if you tell me position, I can find its derivative, and that derivative will tell me velocity.
So we found when it hits the
What?
ground by solving when
Just algebra.
the distance fallen is equal to the distance of the cliff, and then
Yes.
we plugged it into so the velocity is the change of distance over the change of time. And so
Yeah.
then
So the velocity is the same thing as the slope of the tangent line,
this is the slope of the tangent line. Okay, and so
which is another way of saying that. Yeah.
then we just put the two together.
Yeah. So the slope of the tangent line at t equals a is 32a. So at t equals root 5, it becomes 32 root 5. You just put them together.
Okay.
Do you know, I could look at any point in that guy's journey from top to bottom and do his velocity. Let's do that for a minute. Right, I know that d dashed of a, which geometrically is the slope of the tangent line, but it's also now the velocity at t equals a. So let's do a little journey. It doesn't have a very long journey. D dashed of 0 is 32a, so 32 times nothing is nothing. Does that make sense? Yeah, at t equals 0, technically hasn't quite jumped off the cliff, right? So his velocity is 0, right? He's stationary. Now, what's his velocity going to be like in 1 second? Right? Yeah, no, he's probably there, right? That's 1 second, right? And would you agree he's moving? And it's 32a, so it's 32 times 1, so that's 32, and I believe the units are meters, so it's 32 meters per second. Now, what about 2 second mark? Yeah, no, 2 second mark is probably about here. Before we get this number, if you jump off a cliff, either deliberately or accidentally, do you keep the same velocity all the way down to hit the sea, or do you get faster?
Once you hit terminal velocity, that's it.
Stationary. But until you get to that,
You
get faster.
Get faster because of the gravitational pull.
Okay, so shouldn't the 2 second mark be more than the 1 second mark? And yep, he's actually what double D speed. Right. So we actually can. Can you imagine you can follow his entire journey as far as velocity is concerned, from the time he jumped off the cliff to the time he hits the water? And we'll assume things like wind resistance and terminal velocity. You know, we'll do the usual physics thing. We'll pretend they don't exist if they get in the way. Now, you could use this in all sorts of quite advanced ways. Can you imagine that we discovered an asteroid? We do them all the time. If you can plot where an asteroid is for a number of different points, like this is where it is at time equals 0, time equals 1, time equals 2, time equals 3, and you can plug it into a computer and it will make a prediction out of its distance away from you, right? At any given time. But what that also means is, can you then find the derivative of that function? And won't that tell you the velocity of that asteroid? So only knowing where something is actually enough to tell you everything that's useful. And that is pretty much it as far as that question goes. So let's do one more of those, because that's the last thing in this section. Okay. This here is the height of an object. I guess I could call it h of t then, but DLT will work, right? The height of an object after t seconds. So you plug the guy in, and let's say it looks like that. Okay. Now, what's going to happen here is that we're going to try and see what we can discover about the position of this object, and in particular, its velocity. Now, according to the shortcut method, called the power rule, that gets you 0. That gets you what? Negative 2t. And that gets negative 2. There we go. Negative 4 plus 4a. Took me 3 shots to get it. You get a number. That guy gets you negative 4. And this guy is the power rule. 2 times the thing. You got that. Now, that means I could plug in a equals 0, 1, 2, 3, 4, and 5, but one particular one interests me. When is it 0? And that means I am going to solve that guy. And that ends up being at a equals 1. And I know it's there. How do I know that the velocity equals 0 is at this point in this rock that I'm throwing in the air's journey rather than anywhere else? Got a curve. And I'm saying, when is its velocity 0? And we find out that when it's 1 second mark. And I'm saying, well, this is the graph of this. This just tells you what it looks like. And I'm saying it must be there.
Because it's horizontal, the slope.
It's horizontal. And isn't horizontal 0 tangently? Now, we're looking at these things in different ways simultaneously. I'm looking at it as a graph with a horizontal tangent, right? That's one way of looking at it. I'm also looking at it as a moving object, and this is where its paths is. And I know that at that point there, its velocity is 0. And intuitively, it kind of makes sense. If you take a rock and throw it in the air, right? Doesn't it go up? It goes up, right? But isn't there a point where it stops going up and it starts coming down? And isn't there a sweet point where the up and the down meet? And isn't it there? So if you know everything about the position of an object, can't you even tell when it's going to reach the top of the hill? In other words, the highest point that that curve is ever going to get to. And I could, but I'm not going to spend any more time on this moving object. Couldn't I find out what that time there is? And I'm just pretending that it was 5 seconds. If that was 5 seconds, couldn't I plug it into this formula here? Right. And this, well, let's just put in 5 seconds. It's negative 4 plus 4 times 5. And that gets me 16. Can you see I get the velocity at any time I want on the life of this moving object. Don't know what the whew was for. We are now going to do visuals. We are going to look at the derivative as a function. And this couldn't happen soon enough for me. Have you noticed today that I've been doing D-T's and then saying, oops, I should be calling it D-A here because, you know, keep everybody happy. Let's move on to a much more natural way of writing down derivatives. Suppose I have a function f of t and it's t cubed plus 4t squared minus 7t plus 1. If we were being asked to find f dashed of a, right, that basically means the derivative at t equals a. We would do this, we'd use the power rule. Multiply by the power and then reduce it by 1. Multiply by the power and then reduce it by 1. This guy is a special case and the number 1 is a special case, and that would be the answer, right? And then if we wanted to know what the slope of the tangent line or the derivative at 5 would be, wouldn't we plug 5 in here? And if we wanted 7, we put 7 in here. Now, what's f dashed of b? What's the formula for f dashed of b? So that's f dashed of a. What should f dashed of b?
So we do the same power rule as before and just go 6b plus 8b.
Yeah,
Okay.
all that stuff. And
Would the
suppose
7
I
come
said-
down because of the power
Yeah.
rule?
Yeah. The
Okay.
7 is still there. If I said f dashed of c, I'm maybe labouring a point here. I'll do it one more, I'll over labour it. For all intents and purposes, isn't that a just a placeholder for the value of t? Couldn't I have said, find the derivative at t equals b, in which case you get this formula. Find the derivative at t equals c, in which case you would have got this formula. Find the derivative at t equals d, in which case you could get that derivative. You don't need to use these letters. Couldn't I just use this guy? And does it not make a lot more sense when you just have t as the variable in the before and use it in the after? That kind of makes sense. Why do you need this t equals e thing? It just clutters up the whole process, doesn't it? And so when we talk about the derivative of a function, this is an example of a derivative function. You can see it's a function just like every other expression could be. But this is a derivative function. So what does this guy tell you? Well, it tells you the slope of the tangent line of this curve at any given value of t. And so we don't need that at any given value t equals a. We can just say at any given value t. Isn't that just a little bit cleaner? And the t equals a was kind of helpful to get started with because we don't want to get you too messed up with the original and the end, so they kind of separated them out a little bit. But now I think we should be comfortable about it, and it just makes much more sense to think of the derivative function like this. So let's do a couple more of these guys just to get into the swing of how we're going to do derivatives. So just two more. Right, if I was doing the top one, wouldn't its derivative function be using the power rule, negative 4t, add 7? You happy with that one? Now, if the function's called g of t, wouldn't its derivative function, power rule, multiply by the power, reduce it by 1, get -3 because of that guy. Now, isn't that notation just so much cleaner? So we want to do derivatives, we can have these. And I just realized there's something I haven't done yet. If it's called f of x, won't its derivative be f dashed of x? And you get that guy. Isn't it nice and adaptable? Won't your derivative function use the same variable letter as your original? If the thing here is called f, the notation says just call this guy f dashed. What do you think this guy would be called? Suppose I gave you a function g of u and it was this guy. What would we call its derivative? Don't overthink it. It's meant to be a simple question.
G dash U.
Why not? Somebody else tell me the answer. I've done too many of these. Should be able to do the power rule on this pretty quickly.
3U squared minus 2U.
You all feel comfortable about this? Isn't this just a cleaner notation system? Yeah, it's cleaner than this x equals a, t equals a stuff, where I keep on forgetting which letter I should be putting. Now, does it change it? No, the application is exactly the same. Suppose I gave you, oh, I don't know, this function here, and I said, I'd like to know that slope, right, the slope of the tangent line at x equals 7. Well, don't you just plug 7 in here and you've got your answer? Right? Pretty easy to do. Now, since the derivative function is a function, is there any connection between the graphs of the original and the graph of the derivative function? And the answer is yes. There are many connections between the two. Me personally, and it's a preference that I like to use, is that I try and draw the two of them in separate graphs. And the only reason I have to do this is if I try and draw them in the same graph, there's just so much happening that your brain just, it dissolves into a mess. So I've found in my experience that if I separate the original graph from what its derivative looks like, I can see it clearer. When I superimpose one on top of the other, they start interfering in your brain visually and you don't see the patterns. And there is, trust me, patterns. Let's take one of the simplest curves you could imagine. And would you agree that's probably a cubic? Maybe it's a sine function, right? Probably a cubic. And I would like to draw its derivative. And I only have this picture, right? I don't have a function, right? If you just told me it was x squared plus 5x plus 7, couldn't I just do its derivative and plug into the, Desmos and just draw the thing? So we're going to look at this in a different way. So you might say, how do you get the sketch of a derivative function from its original? First thing you do, Do you notice that these 2 points here and here, won't the tangent line be 0? Right, would you agree the tangent line is horizontal, and isn't horizontal means 0, right? 0 slope. Those two guys get dropped down. And I'll overemphasize it. Don't I know that the derivative curve passes through those 2 points? Does that make sense? If these are 0, won't the derivative be 0? Right? So far, so good. Now, this picture has really been split into 3 regions. Region 1, from here to here, region 2, and from here to here, region 3. Now, in region 1, if I pick any point on the original curve, would you agree that its tangent is pointing uphill? Doesn't that make it a positive derivative, right? A positive answer. So in region 1, this is region 1, the derivative is positive. So all I'm doing here is shading above the x-axis, right? That's positive values. Would you agree in region 2 that any point you pick here, isn't the derivative going to be a negative? And in region 3, would it be positive? Are you comfortable so far with the construction of what the thing is looking down here? You happy about the 2 places where it's 0? And in this region 1, it's a positive derivative. Region 2, region 3. Now you might say, well, what am I going to do now? Well, all I am going to do now is draw the best looking curve that starts here, passes here, gets to here, passes here, and finishes up here. And you only do the simplest curve that does it. So don't put extra wobbles in. So if I was doing that, would you agree this thing has to turn? Does that seem like a reasonable sketch of what the derivative function would look like based on the information I managed to glean from the shape of the original function f of x? Does that look like a quadratic to you? What happens to x cubes when you find their derivative? Don't they turn into things like 3x squareds? Don't they turn into quadratics? And doesn't that kind of match what you'd expect it to do? Kind of cool. Now we're going to do a lot more of these because this is the next section that we've actually started. But I want to show you a guy that I stopped a little while ago, and now I'm not going to. I'm actually going to do him. Can you remember the general equation of a quadratic? Ax squared plus bx plus c. It would represent a quadratic, maybe that one there, right? Remember that way back in, God, when was quadratics? 94, 99? Remember that guy? Ax squared, y equals ax squared plus bx plus c. This will get some cobwebs out of your brain. What is the x coordinate of the vertex of a quadratic?
Negative b over 2a.
Have you ever wondered where that came from?
Quadratic formula.
Well, you probably, yeah, quadratic formula, but I mean, quadratic formula is itself just a formula. Have you ever wondered essentially where does that come from? Because I'm about to show you, and it's fascinating. What is the derivative function? Now, I want you to think of A, B, and C as just numbers here. So X is the only variable in town, right? A, B, and C are just constants. So power rule, shouldn't you multiply by the power and reduce it by 1? So 2ax. Isn't that like 7x and 10x? So if you differentiate bx, don't you get plus b? And won't a number like plus 7 plus c, won't that get you nothing at all? Are you comfortable about the derivative is 2ax plus b? Now, at that vertex, which is there, right, isn't the tangent line 0? Great. So this will equal 0 at the vertex. If you subtract b from both sides, and then you divide both sides by 2a, the x coordinate of the vertex. And I got that not by saying, oh, it came from the quadratic formula, because that's just telling you it came from another different piece of magic. Isn't this straight, pure, cut to the chase? You tell me a general quadratic, I can tell you where that is. That's the vertex. And by solving the derivative is 0 at that point, I can tell you the x coordinate of it. If I gave you a cubic, couldn't you find the two places, because there's one up and the other's down, couldn't you find the two places on a cubic where the vertex, no, I'm not sure you should call them vertex, but the local min and the local max live? Say hi and bye-bye. That is cool math. That is just cool math.
It's so satisfying how it all works out. Like, I love it.
You like that, how, yeah.
It is very cool.
It is. It's kind of elegant and neat. I like things that are simple. Even although they might tell you something that's quite complicated or useful, it's nice. I like it.
Have a good day.
You too.
Thank
I'll hang
you.
about, but
Thank
only for a
you.
few moments because I have another
Thank
class to
you.
go to.
Thank you.
Bye-bye.
Professor Robertson,
Yes.
I
Who is talking? Oh, Mia's talking. Yes.
had a question on the 2.7 homework for number 6.
Okay.
It's
Is that a quick one to read out?
y equals x plus 3 over x minus 6.
And it's to find its derivative?
Yeah, find the slope m of tangent line at the point 5, negative 8.
Okay, coming up. Fractions are downright ugly.
Yeah,
They are.
and I've
There's-
worked through it
you-
multiple
you're-
times, and I've thought I've gotten the answer, but I've used up 4 of my chances, so I only have 1.
Okay, so let's make sure we get this one right. So
Yeah.
I'll try to be careful. And did you do the x tends to a or the h tends to 0 method? They both work, but I would do the h tends to 0.
Yeah, that's the one I did.
Oh, good, because they're ugly, but okay. So we are interested essentially in the derivative at 5.
Mhm.
Okay. So it's going to be the limit as h tends to 0 of the function at 5 plus h. Take away the function at 5 all over h. Right? Pretty sure that's where you started.
Mhm.
If you plug 5 plus h, it goes here and it goes here. So what's that going to get me? It's going to get me 5 plus h add 3 over 5 plus h take away 6. Subtract the value of the function at 5. Right, if you plug 5 in here, you get 8. If you plug 5 in here, you get -1. A over -1. A over -1 is -8. Subtract -8. Did you eventually get plus h here? Plus 8.
Oh,
That might have been your.
Yeah, I think that's.
Well, we'll continue the process. Did you just have a -8 there?
Yeah.
Or not an 8? Let me double check because I'm no always perfect. 8, -1. Yeah, it is +8.
Mhm.
So we'll continue it since we're here.
Okay.
These combine and you get 8h plus 8. These combine and you get h, take away 1. And you have a +h and that guy. And now I'm going to multiply top and bottom by h minus 1. And the reason I'm doing that is that fraction has to leave the building, right? We're not going to work with it. So this takes care of that. So we're now going to have the limit as h tends to 0. And there's another place where I can screw up here, so I'll be really careful. If you multiply this term with h minus 1, essentially the h minus 1 kill each other off and you're left with a numerator. And then you've got 8 lots of h minus 1 for the second term. But the good news is that we have no more fractions inside other fractions.
Mhm.
I guess the bad news is that we've still got work to do. 8 and 1 gives me 9h. And 8 take, ooh, that I wasn't expecting. Let me double check that. 8 and 8 is 9, 8 take away 8. And guess what? It's looking really nice now, isn't it?
Mhm.
So I'll cross those two guys out. And I'll now be looking at the limit as h tends to 0 of a 9 on the top and an h minus 1 on the bottom. But that's okay because we can brute force that. We can just put 0 in and we will get the answer
Mhm.
-9.
Oh, okay.